Perfect. Well, thank you again, Jeremy, for your time, and I'll pass it over to you.
Thank you very much, Neil. Can I just check everyone can see the slides? You can, great.
I can see those, yeah.
We don't tend to use Teams very much at the university, so I'm always slightly confused by what people can and can't see. But yeah, that's for a lovely introduction, Neil, and it's a pleasure to be talking to you all today. As Neil said, I'm a statistician by background, so although I do work in all different sorts of health management related areas, including sort of equivalent areas or tangential areas such as some clinical research and some management research that's not related to health. This is where my focus lies, and very much on the quantitative side of these things. So I've been involved in clinical trials, for example, as a statistician. In addition to the sort of work that Neil was talking about in the methodological work, and lots of work with all sorts of surveys, but in particular, as Neil mentioned, the NHS staff survey. What I'm going to talk about today, however, is largely guided by what some of you suggested. I believe that Neil asked what you thought would be most useful in terms of having some statistical input, because obviously an hour is not a massive amount of time to cover the entirety of a discipline like statistics. So because of that, what I'm going to do is focus on a few different topics that are particularly relevant. I'm going to start with some general background, making sure we know why we're using statistics in the first place. That might sound like a very basic question, but actually sometimes that type of understanding where we're coming from helps guide what we're going to do as we go along. So I will talk a bit about different types of study design and types of data, so the front end of this, before we get on to the analysis stage of it. And I will then talk a bit about different types of analysis, making sure that some of the key issues to do with effect sizes, understanding hypothesis testing, and so on are understood, before going on to give some more specific examples of a couple of the most common types of methods seen in, well, across all disciplines, but especially in medicine, so regression and logistic regression. Because if you can understand these, make sense of the outputs, make sense of the results that you read in papers, that's going to take you a long way. So, in terms of the purpose of statistics, why are we doing what we're doing? Well, generally, I talk about three different types of purpose. Some of them are just descriptive. You're simply trying to describe or summarize the data that you have. That can be for all sorts of purposes, but for example, audits would be one such purpose where that would be quite often used. I'm not going to talk in much detail today about descriptive analysis, descriptive statistics, because it's relatively straightforward. I'm more than happy to take questions on the end, questions at the end, if anyone has any, but instead we'll talk more about some of the especially inferential types, but exploratory as well. So exploratory statistics will be when you are, as the name suggests, exploring your data, looking for patterns, looking to see what relationships there might be, what differences between groups or variables there might be, but not things that you've necessarily hypothesized, or not things that you're necessarily trying to generalize too much at this point. That comes much more with the inferential type of statistics, and this is really the core purpose of statistics that many of us need to pay attention to, because anytime we read a study in a journal or equivalent, there's a very strong chance that if they're using statistical methods, they are trying to draw some inference from their data about a broader population. That's what inferential statistics is all about, and it includes different sub-elements of that. So sometimes it might just be estimating something, so using your sample to estimate the prevalence of a disease, or to estimate what the link is between two variables, or what the difference might be between two groups. And by using inferential statistics, what we do is we put some limits on what we can say about that estimation. But sometimes it might actually also be about testing specific hypotheses. Generally speaking, these would be hypotheses that have been derived in advance through theoretical prediction. And then we look to see to what extent that is or isn't true, or to what extent that can or cannot be supported in the data that we're looking at. So I'll talk about that in more detail a little bit further on. However, before we get to that, there are a number of important considerations about any study that we should make. And this applies when you are starting off a new study for yourself, or if you are turning to a data set that you have available to you and you want to understand, or indeed, if you are reading somebody else's research and making sure you can understand what they were trying to do, what sort of data they had, and so on. So the first important question is, what types of data are being used? Broadly, there are two main types of data that we might have, although with different subtypes. So this would include numerical data. Numerical data would typically either be continuous in nature, so theoretically it could take on any particular value within a given range. Sometimes that's referred to as interval data, especially where the measurement isn't quite so accurate, perhaps. Or they can be discrete data that can only take on certain values. By far the most common type of discrete data is count data. So, for example, how many visits to the doctor did this person have? It could be 0, 1, 2, etc. It can't be 1.5. So numerical data is, generally speaking, the most useful type of data we have, because it is measuring something which has a real value. However, sometimes we're looking at things that don't have a numerical value, and in those situations, categorical data is what we're left with. Now, categorical can take on two different forms as well. This would be nominal data. So nominal data is where the categories are just all separate. There's no particular order to them. So we might look at different countries, for example, UK, France, Germany, Italy, whatever. They're just separate categories. Or it could be something which does have a natural ordering. So, for example, it might be something which is measured on a scale. We might have a pain scale measured from 0 to 6 or something like that. Or it could be that you're measuring somebody's grade within an organization, where it goes from grade 1, the lowest grade, up to grade 10, say, at the highest end. So there's a natural ordering there. And it's really important to understand the difference between nominal and ordinal data, because the methods that we use for them, what you can do, are different. At least should be different. And these would generally be slightly more complex methods than what we can do with numerical data, although there is an exception to that, and that is where we have binary data. Binary data being that which is just falling into two different categories, for example, yes and no. Binary data is different because it allows us to do more with it. In a sense, it is both nominal and ordinal. And also we can even think of it as a bit more numerical in a way. If we've got something coded as 0 and 1, and we take the average of it, then that number does have a meaning. It's the percentage or proportion of people who had the answer 1, which might be a yes rather than no, for example, on a question. But the other thing just to mention here, which is really important when it comes to evaluating studies, and evaluating other people's work is, or indeed deciding what to do with your own data, is whether you should turn numerical data into categories. And my main reaction to this is, for the most part, the answer should be no, don't do that. The reason for it is sometimes it may be that you would have two values which are very close together, which would actually then fall into separate categories, whereas there might be values which are quite far apart, which would be actually part of the same category. So you lose information and you're creating an arbitrary split there. I say arbitrary. Sometimes it might not be arbitrary. And there may be a very good reason occasionally for categorizing numerical data. Sometimes, for example, if there's a cut point for a clinical decision about a diagnosis, or something like that, then that would be more justifiable. Or, for example, if we're looking at people's age, we may need to classify children versus adults, in which case, under 18 would be one category and 18 plus would be another. As long as you've got that justification, then categorizing it is more justifiable. But the reason I'm mentioning this at length now is because it's the sort of thing that a lot of studies do, and yet it's not generally considered best practice unless there is that very good justification for it. So do be careful not to fall into that trap. And if you spot others doing it, really question why that's important. The other thing to consider, either in terms of evaluating other studies or in terms of planning your own, is when and how the data are collected. And when I say how, one of the key things is, were the measurement tools reliable? Sometimes you might be collecting purely objective data, objective clinical data, which you would hope the tools are reliable, although that's not always the case. If you're looking at more subjective data, especially if it's collected via questionnaires or equivalent, then making sure that the methods used have been validated is really worthwhile. But also need to consider whether the data is cross-sectional or longitudinal. So longitudinal data is that where the same variables are collected from the same people more than once. Doesn't need to be every single variable at every point in time, but it does need to have some element of repeat measurement for it to be longitudinal. And that's more useful in a lot of circumstances because it enables us to look at change. And where we can see change, we can derive more inferences about the data, sometimes getting more evidence, for example, for causal linkages. But longitudinal data by itself won't be enough to establish causality. For that, you really need experimental data, that which involves manipulation of some kind of intervention. So, and where it's done at random. So, if it's done at random, then we've got some kind of randomized control trial, which is, as I'm sure you're aware, the gold standard for causal research. But if it's just observational data, there's a lot less certainty you would have about that, even if it is collected over time. And the methods you need to help establish causality there are considerably more complex. But one thing I would always say is, if you're doing your own study, it is best to engage a statistician as early as you can in the process, because they will always be thinking about these things from the very start. A few more things I just want to say about evaluating statistical studies. So I've talked a bit about study design in terms of randomized control trials versus observational data. But of course, not everything is created equally. Some RCTs are better than others. If you've got a sort of double-blind, large sample randomized control trial, then that's going to be hopefully very good evidence for you, but you don't always, you're not always in a situation where you can get double blindness, for example. But then within observational studies, there are various different aspects to look at. Quite often we see case control studies, um, those with a particular outcome, have you matched with those without an outcome, and then looking to see what things might predict that. A more recent development in that is what we call propensity score matching, which means that you're matching the cases and the controls in a much more tightly confined way uh, to mean that there's less likely to be any bias in those groups. But then cohort studies, especially the sorts of things that would enable you to look at a group of patients or cases over time, whether that's a matter of days or weeks or years. Being able to track that over time gives a certain level of extra evidence that can be helpful. And I've mentioned cross-sectional studies already. Cross-sectional we might think of as being just a slice at a particular point in time. In reality, it doesn't necessarily have to be that everything is measured at exactly the same point. The key thing about cross-sectional studies is that everything is measured just once, as opposed to measured more than once with a longitudinal study, such as a cohort study. It's important to pay attention to sampling and recruitment methods. Are there any issues in the way that things were sampled which might lead to bias in your sample? Were certain types of person more likely to be recruited to the study in the first place, for example? So I could give a whole hour's session on that alone, but there's a lot to look out for there, as indeed sample size is important. Now, you're probably aware that from a statistical point of view, a larger sample is generally better. We'll talk about reasons why that's the case a little bit later, but obviously from a pragmatic point of view, and sometimes from an ethical point of view as well, you don't always just want to maximize the sample size. So making sure the sample size is justified is the key thing there. Ideally, with a calculation, although if you're using observational or observational or secondary data, it may just be a case of using all the data that's available to you, or was available to the researchers. But with sample size, it's important to know whether it was a large enough sample size to be able to detect the sorts of things that you wanted to be able to detect. It's also important to consider whether there are any confounding factors, and this especially applies in non-randomized research. So especially if you're comparing two groups, were the two groups effectively equal in everything apart from the factor that differs between them? Where they're more likely to be, for example, older people, or people from a different socioeconomic background, or people who were more likely to have a higher level of illness to begin with in one group than the other. And if so, can you adjust for that in the analysis? Always, when you are reading research and trying to evaluate it, pay attention to what claims or inferences about causality are made, because short of an RCT, you're not going to have a study which is going to give very good quality evidence about causality. If you've got longitudinal data, then that might be more easy to say something about causality, but it's still not the same level of evidence as an RCT. So make sure that you don't overinterpret, or the authors don't overinterpret that. And the other thing just to mention about the design is, what don't they tell you? What isn't written up in the paper that that maybe you should be? these days, most leading journals will require you to follow a checklist of some type, whether that's, for example, a consort um, checklist for an RCT, or some other type of um, study with its own checklist. But if there's something which should be on that that isn't, that might be um, a, a reason for suspicion. And then, of course, the last thing to mention is what type of analysis was done. And was this appropriate? Now, obviously, as non-statisticians, I realize that's not so easy to evaluate. And I'm sure if you ask a friendly statistician, they'd be able to help you with this. Again, I could spend a whole series of lectures on different types of analysis, and in fact, in a different part of my work, I do exactly that. In fact, that's how I first met Neil, when he was on one such course. But this is a very simplified table, sort of to help identify what type of analysis might be appropriate in different circumstances. And I'm not going to go through all these now because we don't have that long. But I will just point out that there are all sorts of other variations of these that we could use in different circumstances. And I'm going to, a little bit later, talk about the two which I've put in bold, which are multiple regression and logistic regression. So just to clarify when these ones should be used, for example, it's when we are looking to compare variables, which is a very general term. What do I mean by compare variables? It's basically to see whether one variable, or sometimes more than one variable, is linked to another. So most of the time we would have a dependent variable when we're trying to explain, and that variable, according to this table, would either be numerical and follow a normal distribution, or numerical will not follow a normal distribution, or it could be binary. So if we've got a numerical and approximately normally distributed outcome, then multiple regression is likely to be a good way of doing that. If the outcome is binary, then logistic regression is likely to be a good way of doing that. But I don't think it would be a good use of time to go into much more detail about this right now. So I'm going to come back to talking about the normal distribution and so on in a few minutes. But given we're now sort of talking about the analysis side of things, it's worth just spending a few minutes thinking about what we get out of the analysis and how you would treat that, and how you would understand what comes out of it. Because broadly speaking, there are two different types of things that you would get out of analysis if you are doing inferential statistics. The first is some kind of effect size. So effect size just means something that describes how big an effect is. And there are different types of effect size. The most straightforward one to understand is what sometimes is called the raw or unstandardized effect size. For example, the difference in mean between two groups, or a regression coefficient. I'll explain regression coefficients in a few minutes. Or it could be something else where the numbers represent something about the actual data that you are looking at. Then there are also standardized effect sizes, and probably the most common, or the most understood type of a standardized effect size would be a correlation coefficient. Correlation simply measures the strength of association between two variables, but it does it on a standardized scale, so that it's always going to be between 1 and -1, with 0 representing no relationship, or strictly no linear relationship. There are other types of standardized effect sizes for different situations as well. So for example, if you're looking at differences between groups, the effect size called D, which is basically just the difference divided by a common standard deviation, that can be used to represent whether it's a small or medium or large type effect there. Standardized effect sizes are quite popular in some fields. Certainly in medicine, they are not uncommon, but they are less well represented and probably less well regarded than the raw or unstandardized effect size. And that's because if you've got variables which are measured well, if you're measuring real quantities, then the unstandardized effect size gives you better information, as we'll see in a couple of minutes. There's also a third type of effect size, which I'd call a statistical one, which is basically saying how well a number relates to a known statistical distribution. So sometimes you'd see T or F, or others there. And chi-squared would be another common one, for example. These are useful from a statistical analysis point of view, but don't really have much meaning to the wider audience. So that's not so useful to report. However, reporting at least one type of effect size is really important. And this helps you establish the clinical or practical significance. However, what it doesn't do is tell you anything about the statistical significance. And I very deliberately talked about the effect size before talking about statistical significance, because the effect size is really the most important thing to get out of this. However, statistical significance is also a very important issue if you are using inferential statistics, because this tells you whether or not there's evidence of a real effect being there in the wider population. And if you are testing hypotheses, what you would effectively do is test a null hypothesis, in other words, one where there is no effect, and look to see whether the data is far enough away from that situation to give you evidence that it's very unlikely the null hypothesis is true. That gives you the p-value. The p-value is the probability of observing data which is at least as extreme as you've got in your sample if the null hypothesis is in fact true. So if the p-value is small enough, what that means does depend on the context, but for example, below 0.05 is a fairly standard level of significance, then we say that the hypothesis, the null hypothesis, would be rejected, and as long as the data is in agreement with this, you know, our original hypothesis, our original expectation would be verified, they would be supported. So if we find that there is no statistically significant effect there, then it doesn't really matter whether the original effect size has clinical significance or not, because we don't know for sure that it's not actually 0. But one way we often combine these two is using confidence intervals. Now, some fields and subfields are really good about always reporting confidence intervals, and some are not. I have it as one of my missions to try to increase the use of confidence intervals across all the fields that I work in. In most leading medical journals, at least, they would be reported as standard, which is good. But the reason this combines the two is because it tells you something about the effect size, the raw, or sometimes even the standardized, but usually the unstandardized effect size, as well as giving you something about the level of certainty of that effect size. So for example, in the statement I've put here, the difference between treatment A and treatment B in terms of systolic blood pressure was 3.5 millimeters mercury, and 95% confidence interval 1.1 to 5.8 there, meaning that with 95% confidence, we could say that the actual difference is somewhere between 1.1 and 5.8. Now, what I just said is not quite the strict statistical definition of a confidence interval, but it's close enough that it makes sense to understand it that way. So being able to show that confidence interval and to show whether it, for example, includes 0, which in this case it doesn't, gives you really good evidence of when something would be both statistically significant, but also giving you an idea of the possible range of the effect size. It might often range from something quite small to something quite big. The larger the sample size you have, the smaller the confidence interval will be, the more certainty you would have about an effect. And the testing of a hypothesis is more likely to lead to a significant result if you've got a larger sample size. More importantly, or perhaps equally importantly, it's more likely to lead to a significant result if there is a real effect in the wider population. You're less likely to fail to support a hypothesis that should be supported. So that's why we do strive for a larger sample size, at least one of the reasons. We'll come to another in a moment or two. Now, in the survey that Neil sent around, I think some people were asking for a little bit of information about the assumptions behind tests. Because this is also a really important thing to understand if you're trying to evaluate whether a test, particular method analysis, was important. And most statistical tests we use do have some assumptions about the data behind them. There are some which don't, and some which vary the assumptions. I'll come on to talk about those just at the end. But in terms of those that do have assumptions, here's an example for regression analysis. And I'll say a bit more about regression analysis in a couple of minutes. But regression would assume that the relationships you're looking at are linear, or if they're not linear, then you're building that into your regression equation already. But they also assume that the residuals are independent and normally distributed. So it's actually the residuals, which are the difference between the observed values and the predicted values, that should follow a normal distribution rather necessarily than the original variable, although it's generally true that if one does, the other will as well. There are exceptions to that, however. When it says the residuals are independent, it means that basically knowing how close one case was to being predicted correctly shouldn't give you any more knowledge about whether another case is likely to be predicted correctly or not. The variance of the residuals should be independent of the predicted values. We don't see any link there between whether it's a low or high value and how varied the residuals are. That's the assumption sometimes known as homoscedasticity. And then also that there are no problems with multicollinearity, so extra large correlations between your predictor variables, or outliers, so those cases that have an undue influence on the result because they are very different from a lot of other cases in their values. So that's just a quick whistle stop tour through the assumptions for linear regression analysis, and I don't expect you to have necessarily understood all that or taken it all in or to remember it. If you've studied regression analysis before, that may ring a bell with you, but if not, then I wouldn't worry about it because it won't be the same for other methods anyway. The important thing is knowing that there are assumptions that should be tested, and if assumptions are not met, it casts doubt on the reliability of the findings we get, especially anything to do with inferential statistics. So standard errors, which are a measure of how accurate an estimate is, they would be biased if these assumptions are not met. So when we do a test, we would try to check that they are valid. However, it's also worth noting that larger samples can cope with some deviation from these assumptions. And when I say larger samples, we're talking at least a few hundred cases to be sure about this. But this is another reason why a larger sample can be beneficial, because in that situation, even if the assumptions aren't perfectly met, we're still likely to get quite good results out of it. So in the final few minutes, I'd just like to talk about these two methods of linear regression and logistic regression, as I mentioned earlier. So just a few words about what regression is for. Basically, it's trying to explain one outcome variable in terms of one or more predictors. If you've got one predictor, which is simple linear regression, it's as simple as plotting things and fitting the a line of best fits there. Well, I say fitting it, obviously the regression method chooses what line that would be to minimize the technically it minimizes the sum of the squares of the residuals, but basically it's trying to get as good a fitting line as possible. If you've got more than two predictor variables, you can't draw it quite so neatly as that, of course. But it gives us an equation, a regression equation of the form y, which is our dependent variable, is predicted by some intercept a, which is where the line crosses the y-axis, plus some combination of b1 x1, where x1 is your first predictor variable and b1 is a regression coefficient, which is estimated, and then plus b2 x2 and so on. So these regression coefficients effectively tell us the slope of the line. In other words, they tell us as the variable x1 increases by 1 unit, what do we expect to happen to the outcome? In the example we've got on the plot here, where it's plotting a mother's weight against the baby's birth weight, a regression coefficient here would tell us for a 1 pound increase in the mother's weight, how many grams more would we expect the baby's birth weight to be on average. So these all have that meaning, and that is interpreted when everything else is held constant, which is an important part of that consideration. The other thing you see at the end of this equation, this epsilon, the Greek letter epsilon there, just represents the residual or error. So it's acknowledging that no line is likely to fit the equation, or fit the data, I should say, perfectly. And in fact, we can measure the fit. We often use a measure called R squared, which technically is the proportion of the variation in the outcome, which can be explained by the predictor variables. So that allows us to see how well a particular regression model will fit. And we sometimes use a statistic called adjusted R squared, which makes an adjustment for the number of predictors you've got in the model, which allows easier comparison between different models. And regression is especially useful to us because it's very flexible. It's used for testing not only sort of basic models like this, but also things like mediation, where we're looking for an explanation between two variables, explanatory variable in the middle of two variables, moderation, where we expect some kind of interaction between variables, and so on. Regression is used for all these things. Let me just briefly give you an example from the literature, so we can check that we understand what this means. This is an extract from a paper by Brian Jarman and colleagues, published in the British Medical Journal quite a while ago now, but it's 1999, which is, gosh, 25 years. but I think I still use it as an example because I think it's really helpful for understanding. And in fact, what they did is they fitted two different models here. We'll just concern ourselves with the model B for the moment, which is where they looked at predictors of mortality amongst emergency admissions in 183 hospitals. And you see there it gives us an adjusted R squared of 0.5. So it explains quite a lot of the variation in the data, but by no means all of it, as we would expect. But just to pick a couple of things here, well, we see that all 5 of the variables are statistically significant because the p-value column has values which are either less than 0.001 or, in the case of the standardized admissions ratio, 0.003, but all clearly below the 0.05 level that I mentioned is fairly commonplace earlier. But let's take a look at, as an example, the first predictor there, the number of hospital doctors per 100 hospital beds in that particular year. So that has got a regression coefficient of minus 0.51. What that means is that on average, as the number of hospital doctors per 100 beds increased by 1, say going up from 5 to 6 or going up from 20 to 21, it doesn't really matter where we choose because it's the same linear effect, then we would expect the outcome, which is the standardized mortality ratio, to decrease by 0.51 units, which is equivalent to saying roughly about 0.5% fewer deaths on average. And we've got a confidence interval around that going from minus 0.65 to minus 0.38. So the 0.51% is our best estimate of what the effect is in the broader population, but we would say that it's likely to be somewhere between 0.38% and 0.65%. That is how we would go about interpreting that regression coefficient. And that is with everything else held the same. So these other variables in the equation, percentage of cases with comorbidity, percentage of live discharges, etc., if they all stay the same, but the number of hospital doctors changed, then that would be our best estimate of what would happen to the outcome. We have to be careful, though, that this is observational data. And although I might have described that a moment ago in a way which suggests some kind of causality there, and of course it's entirely plausible that this would be a causal relationship, at least in part, we can't say that for certain just from a regression equation because it's observational data. We haven't done an experimental study where we change the number of hospital doctors per 100 beds in one group and not in another. So the other type of analysis I just wanted to mention in a little bit more detail was logistic regression, which is what we do where the outcome is binary. So where the outcome is binary, we can't use a regression equation because we can't get a plot which looks a bit like that. So instead, what we use is a transformation. Specifically, we tend to use the logit or log odds transformation of the probability of an event happening. So that event might be a death, it might be whether or not somebody visits their GP, it might be whether or not somebody gets promoted, it might be whether or not somebody has a child, anything that has 2 possible outcomes. And the logit of the probability is defined as the log odds, that's the natural logarithm, that's what the ln means, of the p divided by 1 minus p. The odds of an event being the probability that it happens divided by the probability it doesn't happen. And that is then set as equal to, well, if it's a simple case with one predictor, a plus bx, or if you've got multiple predictors, we'd have more x variables on there as well. So in some senses, this is quite similar to linear regression. It's just we can't draw that more direct comparison, and the coefficients we get out of it are less meaningful. The b in this equation can't be directly interpreted. So instead, we use what's called the exponential of b, which is the statistical number e to the power of b, and this is called the odds ratio, because this tells us the proportional change in the odds for a 1 unit increase in the independent variable. So as a variable goes, say, from 2 to 3, what happens to the odds of the outcome event occurring? And just as a very brief example, I'm not going to go through this in quite so much detail, but from another BMJ paper, which is looking at use of different stimulants and risk of crashes in long distance drivers of commercial vehicles. So it was a case control study. But the thing that we're looking for here is the adjusted odds ratio on the right hand side, which tells us that, for example, the use of a caffeinated stimulant, we see in the yes row there, that has an odds ratio of 0.37, and the adjusted bit just means once the other variables are taken into account, meaning that people who use a caffeinated stimulant have odds of a crash which are about 0.37 the times of those who don't. In other words, the odds have decreased by a factor of about 63%. But it's just really important to talk about the odds here rather than the probability. It's very easy to think this is referring to probability, but odds is not the same as probability. And it's amazing how many people fail to remember that when they are writing this up. So that's another thing just to pay attention to. It's slightly inconvenient, that, because we think about probability in a way which is much more intuitive to thinking about odds. In fact, most of us wouldn't really think about odds at all much of the time unless we're used to looking at a lot of clinical research or alternatively gambling. But for the rest of us, it's not something which is quite so intuitive. The other thing I'm just going to mention here is that in terms of illegal stimulants, there's an odds ratio there of 0.68, but the confidence interval here, 0.27 to 1.67, includes the value 1. And that's a relevant thing because for the odds ratio, the value of 1 is kind of the null value, the one which means there's no effect. So that would mean that the use of illegal stimulants is not a significant predictor of crashes in this case, because if you multiply something by 1, it stays the same as it was. So that's a sort of a brief look at logistic regression. I'm just going to say very quickly about what you do if the assumptions are not met, because this is something that also came up in the survey, I believe. Well, there are various different options. So non-parametric tests, which are those which don't make assumptions, can be used. Generally speaking, they're much less flexible, much less powerful. So although they're useful in some circumstances, they wouldn't be a replacement for some of the types of analysis that we've just been looking at. Generalized linear models is where we use some other kind of transformation to create a model a bit like a regression one. In fact, the logistic regression we looked at is one type of generalized linear model. If we've got a time to event outcome like survival, then Cox regression or Kaplan-Meier analysis is a good way around that. Or we can sometimes use other variable transformations which can get around something not being normally distributed. And as I said earlier, if we've got a large enough sample, then we may be able to get around some of these assumptions in any case. But you do want to choose the right type of model for the type of data that you've got. And of course, if you're still in doubt, or even if you aren't in doubt but want just some confirmation, then consulting a statistician is generally the best thing to do. So I'm going to stop there. We've got about 5 minutes for any questions that you might have.
That's great. Thanks, Jeremy. Does anyone have any questions? just while we're waiting for anyone to pipe up, but I did have one. If you're thinking about degrees of freedom, how do you best explain degrees of freedom to people? And with some of the more advanced non-linear models, you start to get degrees of freedom that aren't a whole number. How can you get degrees of freedom that are not a whole number?
Okay, so degrees of freedom is a complicated one to explain in general, but in some cases a bit easier to understand. So degrees of freedom basically means the number of different things you can adjust in a model given the parameters that you've got. And very often it's linked to sample size, or sometimes it's linked to the number of categories in a variable, depending on what type of thing you're doing. The reason it's important is to do a statistical test. What we normally do is we compare a particular statistic with a known distribution, but those known distributions have different forms with different numbers of degrees of freedom. So that's why it's important to know about them. But in terms of the why we get non-whole numbers, basically that's because at that point we're no longer sort of doing exact statistics, but instead doing estimation of different types of model using sort of numerical methods that aren't based on equations, but are based on trying to estimate something as well as possible given the parameters we know about. It's a little bit difficult to explain in abstract terms, but effectively it means it's the best guess at what the degrees of freedom should be, and then we just have to let the software deal with what that means in terms of calculating the statistics we need.
That's great, thanks. Does anyone else have any last minute questions? I appreciate Jeremy's got to be off by 3. So if there aren't, then we'll let you go. Thank you so much, Jeremy. That was really appreciated. Kindly recorded. So if anyone wants to catch up with that, it is available on the Bridge Pediatrics X Twitter feed. And please do spread the word to anyone who might have missed. But thank you very much, Jeremy, for your time. It's much appreciated.
Great, thank you.
Thank you. If people could please fill the feedback form, the link is in the chat. That would be really useful. Thank you.